Hi guys, welcome to another lecture video. Today we're going to be talking about the additive NTT and also Reed-Solomon codes, but specifically in the context of binary fields being the underlying field rather than some large prime field. Before we dive into this, I will say that I think that the best way to approach this is to read the notes in conjunction with listening to me explain them. The notes will be more precise. However, I might give the added benefit of sort of giving you another reminder of what some of the underlying concepts are when you're trying to read some complicated math expression, and maybe might recall things that might not be in the notes. So I'll be more verbose, but the notes will be more precise, and I'll also be more hand wavy, but the notes again will, really be the mantra with which you can fully have a correct description of whatever it is that we're trying to discuss. Before diving in further, I will give a disclaimer. This is probably a very dense lecture, and I'm going to be trying to fit in a lot of things into a little bit of time. So no matter how well I explain this, I do think that this is the type of thing where you're going to need to really struggle with this and sit down and try and learn this. But I do think it is well worth your time to make that investment, especially if you're planning to be at this company long term, because this will be a theme that does show up in a lot of places. The Fry protocol, for instance. Anyways, the other thing that I want to say is that if you haven't watched the Zero Check lecture series, I would recommend that you watch that first, especially the first lecture where I talk about some mathematical preliminaries, because it'll be very difficult to follow some of the concepts in this work if you're not comfortable with what a polynomial basis is or what a Lagrange basis defined over some input domain means. If those things are slightly foreign concepts to you, I would recommend going back to that first lecture where we talked about mathematical preliminaries and really ironing out any misunderstandings that you have there. Without further ado, let's get into this additive NTT and Reed-Solomon over binary fields lecture. So recall that normal NTT is over a large prime field, a large finite field, which works by, this is actually already a mistake on the first sentence. Let's say a large finite field. Large finite field, and it works by transforming monomial basis coefficients of a univariate polynomial to Lagrange basis coefficients over a carefully selected domain. So what does that mean in English? What that means is suppose the transformation is supposed to be defined for univariate polynomials of degree strictly less than 2 to little l, i.e. this polynomial ring. Then if we take an arbitrary polynomial in this polynomial ring, and we represent it with its, say, coordinate vector with respect to the monomial basis, then this transform will take this coordinate vector and turn it into this other coordinate vector b, which is with respect to the Lagrange basis defined over some domain D. And Lagrange basis coefficients, once again, are just evaluations at specific points over the domain D specifically. When D is equal to this very specific subset of the underlying field, then we are able to do this NTT and INTT, the traditional versions, in a nice way with this quasi-linear algorithm. So if you let n be the size of the input, in this case that's 2 to the L, then this is n log n. And that allows us to change between this coordinate vector and this coordinate vector, and actually vice versa using the inverse transform. That's cool. This thing here, though, is the 2 to the Lth root of unity, and it has to be an element in the underlying field. So there has to be some element that the minimum power that you must raise it to in order to get back 1 is 2 to the little l. Unfortunately, such an element will not exist in our binary fields. And so we'll have to think of a new way to perform this very efficient change of basis into Lagrange basis specifically is what we want for Reed-Solomon codes. More on that later. But enter the additive NTT. Basically, the reason we're doing all of this is because the normal NTT methods do not work for binary fields. So here's an outline of what we're going to be covering today. First, we'll talk about subspace polynomials, what they are, what their key properties are. Then we'll introduce this alternative basis for univariate polynomials called the novel polynomial basis. So instead of using 1x, x squared, x cubed, etc., and thinking about the coefficients on that, we'll have coefficients on these weird, funky polynomials themselves, like 1x, x squared. These are all polynomials. And your polynomial basis will be completely different. Then we're going to talk about the recursive structure that this novel polynomial basis gives us, and we'll kind of look at some interesting things about them. And section 3.5, we'll talk about this algorithmic structure, and we'll kind of talk about how like the algorithm to do this transform has some really nice structure when you're working with the novel polynomial basis and trying to turn it into a bunch of evaluations, i.e. like the Lagrange basis coefficients. Finally, after like sort of doing all of this machinery and maybe noting some key structural properties, we'll talk about how we can actually do the forward transform. After that, we'll take a step back. We'll talk about linear codes. And during this section, I'll jargon bust a little bit. I'll tell you some interesting facts about linear codes that are useful for snark construction specifically. We'll talk about Reed-Solomon encoding, and then I'll do a quick note on the inverse transform and Reed-Solomon decoding. The Reed-Solomon encoding section, this will sort of tie together everything you've learned in these previous sections, and we'll show you how additive NTT is basically like a sub-step in doing the Reed-Solomon encoding algorithm. I really do think it is important to learn section 5. It feels kind of out of place with the rest of these, but I'm sort of throwing it in there because I want you guys to feel comfortable with, you know, the terminology behind linear error correcting codes. With that said, let's talk about section 1, subspace polynomials. So we're going to fix a binary field L of degree R over F2. That means that L is isomorphic to F to the R. All finite fields of the same cardinality size are isomorphic. I'm throwing words at you because maybe you'll understand, absorb some of them. Okay, L is a binary field of degree R over F2. That's actually hidden in the sentence is that we can view L as a vector space over the field F2, and it's an R-dimensional vector space. That means that it has a basis, which is R elements from L, and everything in L can be represented as a unique linear combination of these basis vectors where the coefficients themselves come from F2. So this is all just sort of unpacking what a vector space is. If you're comfortable with all that, then it's just L can be viewed as an R-dimensional vector space over F2. Cool. So now let's talk about some subspaces. UI is the subspace that is spanned by these first I basis vectors. And so the span is basically like all of the elements that you can get by taking linear combinations of these basis vectors, these first I basis vectors. And the linear combinations, again, the coefficients are all coming from F2. Cool. And we now can talk about what a subspace polynomial is. So subspace polynomial is something that splits completely over L, and its roots are each multiplicity 1. They form an F2 linear subspace of L. Rather than unpacking that, I'm going to show you an example of a subspace polynomial. And this is the only example we'll really care about. We'll talk about Wi of x. This is the polynomial, which is defined to be this large product of x plus little u for each little u in the ith subspace. Okay, and then we can talk about a normalized variant of it too, which is basically where we scale it, we divide it down by some constant, and this gives us the nice property that w hat I beta I is always equal to 1. We're going to call this the normalized variant. It turns out that it's very nice working with that. The roots of the subspace polynomial are exactly the elements of UI, and they all appear with multiplicity 1. Cool. Now, note maybe I'll make a quick note. We're working over binary fields, so everything is characteristic 2. That means for any element, that element plus itself gives you 0. So if you pass in as like capital X, like some value that's in UI, you'll get that value plus itself as one of the factors. The value plus itself is going to be 0 as a factor. So the roots of Wix are in fact just UI. Now note, W0x is this thing, but for all little u in U0. So what is U0? U0 is the subspace of L generated by the first 0 basis vectors. So there's only one element in it. That is the 0 element. What can you make with nothing? You can make only 0 with nothing. So that means it's this, which is equal to this, which is this. That basically is just going to say that W0 of x is just the identity map. That's all I wanted to say about that. Note that the degree of Wi of x is equal to 2 to the I. In fact, this degree is equal to the size of the ith subspace, ui. The size of the ith subspace is basically how many elements can I make from this, right? And how many elements can I make from this if my coefficients have to be f2? Well, I have 2 choices for my coefficient for beta 0, etc. I have 2 choices for this last, for the coefficient for this last basis element. I have 2 to the I, 2 times 2 times 2, 2 choices every time. 2 to the I is the size of ui, and since like every single u in ui is contributing like 1 to the degree of my subspace polynomial, the ith one is 2 to the I. Great. Here's a lemma. Ui plus 1 is equal to the disjoint union, actually, of ui and this thing, which is basically shifting everything in ui up by beta I. Why is that true? Basically, you can think of all the elements in ui, and half of them will have beta I set to 0, and that corresponds to this set. And the other half will have beta I set to 1, and that corresponds to this set. Now that's kind of a useful lemma because it allows us to prove this identity, that wi plus 1x is indeed equal to this. Why is that true? Well, this is equal to that definitionally, and this is equal to that definitionally, and this is equal to that definitionally. And these things are equal to each other by this lemma, right? Like u and ui plus 1, half of them are just in ui, and half of them are in like ui but bumped up by beta I. So this is equal to this, which is equal to this, which is a proof that this identity is true, and this identity will come up much later. But just highlighting it now, you can come back to this section when that identity does come up if you're curious. Okay, let's fix a little b in the range 0 to 2 to the r minus 1. And let bi basically be the ith bit of little b, where b0 is going to be the least significant bit, and this one's going to be the most significant bit. Then I can say that b is equal to this. I mean, that's the definition of the bits, binary representation. Then we can denote omega b is equal to the element in L, which is I chose the coefficients of these betas exactly as my bits. My bits are my coefficients. A bit 0, 1 is the same thing as an f2 coefficient. And you take the dot product, and that gives you an element in L, our binary field. Thus, L is equal to, as sets, this set right here, omega b, for every b in 0 to the r minus 1. This means that there's like a 1-to-1 very natural correspondence, actually, between our binary field L and r length bit strings. Another quick note, if you like look at this like definition of omega b here, you'll see that omega 2 to the I is nothing other than just beta I. Cool. And now we will summarize some important results related to the subspace polynomial. For all pairs of elements in L, x, y, pick any of the like subspace polynomials. It is linear, right? So it's a linear map, which means that we can do this is equal to this. Since it's an F2 linear map, that means that this property holds. Normalizing it, dividing out by some constant, doesn't actually change the fact that it's linear. Cool. Again, pick any k, so basically pick any like subspace polynomial, and then pick any element that is smaller than 2 to the k, right? Kind of referring to elements of the binary field L as like numbers now. That's fine because we have this one-to-one correspondence, and I'll continue to talk like that. The subspace polynomial evaluated at omega b is going to be equal to 0. Why is that true? Omega b, it's basically, it can be, you can think about what is its binary representation, basically what is its coefficients for the basis vectors. And its coefficients for the basis vectors are 0 from beta k onwards. And sum of beta 0 up to beta k minus 1 will be 1s. Since this property is true, I can think about omega k, wk of omega b is basically being equal to like wk of beta 0 plus wk of beta 2, etc., plus wk of beta k minus 1, let's say. And I can sort of like break it up into its basis constituents. So let me actually show that. Let's say, for example, WB is equal to like beta 0 plus beta 2 plus beta 3. Then WK of omega B is equal to WK of beta 0 plus WK of beta 2 plus WK of beta 3. These are all going to be 0. Maybe I didn't even need to do this roundabout. Maybe I could have just told you that omega b lives in UK. And therefore, it's a root of WK. Okay, great. Now for any k in this range, we can relate the k plus 1th subspace polynomial with the kth subspace polynomial. This one only applies to the non-normalized variant, unless your binary field is the like represented in like the Cantor basis, but that is getting ahead of ourselves. Generally, this only applies to the non-normalized variant. This identity is true. Cool. And that concludes section 1. So pause here, make sure that you understand all the content in this section, review these notes, and when you're comfortable, we will move on to section 2. Now let's talk about the novel polynomial basis. So from before, we have fixed in binary field L as a degree R extension of F2 with the following basis. We're now going to fix another parameter, little l, in 0 to R minus 1. And we'll denote as this the ring of polynomials with coefficients from the field L of degree less than 2 to the little l. So this polynomial ring is formally defined to be all the polynomials where the degree of p is less than 2 to the little l. Okay, a little bit overkill, but maybe I'm just being verbose. Okay. Now, this polynomial ring, which maybe that terminology is confusing, this like set of polynomials with L coefficients of degree at most strictly less than 2 to the little l, this ring is in fact a 2 to the little l dimensional vector space over L. Okay, so let's not get confused because there's two vector spaces at play here. There's the first vector space, which is L, the field is a vector space over its smaller field, its subfield F2. And then there's a second vector space, which is like this polynomial ring, set of polynomials of with a degree bound, is a vector space over L, our bigger binary field. Two vector spaces at play. This one is an R-dimensional vector space, and this one is a 2 to the little l dimensional vector space. Great. So yeah, if this is a 2 to the little l dimensional vector space, it must have a basis of size 2 to the little l. natural basis would be the univariate monomial basis, 1x, x squared, blah, blah, blah. However, we do not know a theta of L times 2 to the little l algorithm to change basis between monomial and Lagrange. So that's a problem. Instead, what we're going to do is we'll define this new polynomial basis, this novel polynomial basis, which is defined like this. So the ith polynomial basis is going to be this. The ith polynomial is going to be this. What is this? So we take I, we look at its binary representation, and if the kth bit of I is equal to 1, and if and only if, then we will include the kth normalized subspace polynomial as one of our factors in this grand product. Okay, what is that doing? Recall that, like, if I take polynomial p and polynomial q and I multiply them, the degree of this total thing is like the degree of p plus degree of q. Okay, and what is the degree of, like, this w hat k? It's 2 to the k. So the degree of xi is in fact going to be like, I'm basically adding 2 to the k whenever the kth bit of I is equal to 1, which means that the degree of xi is going to be exactly equal to I. And now I have this thing, which admits a L basis for this polynomial ring. L basis means that every polynomial in this ring, degree bound strictly less than 2 to the little l with L coefficients, can be written as a unique linear combination of these polynomials where the linear combination coefficients come from L. Okay, so I have not proven that this is indeed a basis for the univariate polynomials with this degree bound. I have not proven that. However, you would expect that each of these guys has to have like a different degree, because I should have some way. Let's say that, I didn't have any of these polynomials as degree 7, right? I should have some way of creating like a degree 7 polynomial as like a linear combination of these other polynomials. So it is good that each of the xi's give us like a unique degree in the range 0 to the 2 to the L minus 1. That is not a proof. That is necessary, but that's not sufficient for it to be a basis. What I will say is that we will kind of in a roundabout way prove that this is a basis when we talk about how additive NTT works. And the fact that there is like a forward transform and an inverse transform means that this like change of basis mapping is invertible. And if the mapping is invertible, or equivalently the matrix defining this linear map has a non-zero determinant, then that takes us from like something we think is a basis to something we know is a basis, then the something we think is a basis is indeed a basis. Basically, you just need to check that this spans this ring. Anyways, I'm sort of yapping, so I will move on from here, but just take my word that this is indeed a basis for this ring, and we call it the novel polynomial basis, and here's how it's defined. I will highlight this because it's important. Great. I would recommend again that you pause here, make sure that you fully understand all of the content in this section before we move on to section 3. Move on to section 3. So now we're going to talk about the recursive structure of this novel polynomial basis that we had just defined in the previous section. Once again, we have fixed a binary field L with degree R over F2 with the following basis. We fixed some parameter little l in the range 0 to R minus 1 inclusive. And we are now going to fix an arbitrary polynomial, capital D of x, which, interestingly enough, is represented to us not in the univariate monomial basis, but in the univariate novel polynomial basis. for the polynomial ring with this degree bound of strictly less than 2 to the little l. Awesome. So we basically have like this coordinate vector is how we'd represent it. D0, little d0 up to little d to the l of -1. Okay. We're now going to define these weird looking operators. And delta ML is how I'll refer to this thing. Delta ML of x is equal to d of m, so the mth coefficient in our coordinate vector for this arbitrary polynomial. And this is sort of like the base case. This is degree 0. And then here we have this other polynomial, delta mi of x is equal to this thing, which is like a recursive construction, which uses delta m I plus 1 of x, uses delta m plus 2 to the I plus 1 of x, and also some weird factor here. Okay, so we have this lemma that the degree of delta mi of x is at most 2 to the l minus I minus 1. Why is that true? Well, when I is equal to L, this value is equal to 0, and the degree of this is indeed 0. Then as we bump I down by 1, we can see that what happens to the degree, well, this is going to be constant, this is going to be constant. So now the degree is equal to 1, at most 1. And then from there, it just sort of like keeps on kind of doubling, right? Like from this term, we're doing like a 1 times, yeah, I mean, I'll let you sort of unwrap that induction proof by yourself. It's not very hard. The key takeaway, I don't want to get too bogged down in too many details, is that delta mi of x has degree at most this. Another thing I'll mention for delta mi is it's only well defined if m is representable as an I-bit integer, unsigned integer. So m has to be in the range of 0 to 2 to the I minus 1 inclusive. I'm now going to make a claim without proof. The delta 0, 0 of x is actually capital D of x. Seems crazy. So capital D of x is actually just this coordinate vector dot producted with the novel polynomial basis. And we can, actually expand out this dot product and group things in kind of a weird looking way. And we get this expression here. This actually turns into delta 0, 2. Recall this is like delta 0, 0, delta 0, 3, delta 4, 3. This is delta 2, 3, delta 6, 3, etc. And if you use this rule, you can see that this turns into this, and this turns into this, this turns into this, and this turns into this. Similarly, you can apply the rule again, and we actually get that this whole polynomial, capital D of x, is indeed equal to delta 0, 0 of x. And I therefore have presented a proof by example. So hopefully that suffices for you and your curiosity. Great. So we've defined this weird looking operator, and it's really interesting because delta of ML will give us the coefficient in novel polynomial basis. But delta 0, 0 is actually a polynomial of degree strictly less than 2 to the L that gives us like the evaluation at x at your input. Fascinating. It's almost like we're turning coefficients somehow into evaluations if you replace x with like a specialization rather than a variable. Weird. Okay. Maybe it's hard to see what's going on too clearly, but as we look at more examples, it'll become more clear. Quick lemma. Delta mi of x plus y is equal to delta mi x when y is really small. When y is basically like something that only uses the first I basis vectors, then delta mi x plus y is basically delta mi x. Why is this true? You can prove it by induction on I. You can read the notes. Proof's not very interesting. It's just a standard induction on I, starting at L-1 and working backwards. Great. So that concludes the talk about the section about the recursive structure of the novel polynomial basis. I again recommend to pause here and try and feel comfortable with what we've talked about in this section before we proceed. Okay, the next section is about the algorithmic structure of the novel polynomial basis, specifically when we're trying to do the forward transform. So we've fixed a binary field L at this point of degree R over F2 with the basis. We fixed a parameter little l in this range, 0 to R minus 1. We're considering the 2 to the little l dimensional capital L vector space of all polynomials with L coefficients that are strictly less than the degree bound. And we have fixed some arbitrary polynomial, which is represented in novel polynomial basis. Our goal is now to exploit the recursive structure of this novel polynomial basis to build an algorithmic structure for our goal of efficiently doing the change of basis from some basis into some Lagrange basis. Okay. How we're going to do this, we're going to fix a shift parameter. But before we talk about how we do this, we're also going to fix a shift parameter s, which is in the range like 0 to 2 to the R minus 1. It's basically like fixing like some field element in the field L. More on this later. For now, when we're just talking about this, imagine s is 0. It'll be easier for introduction. Cool. We're going to talk about some more weird looking sets now that all relate to one another in some weird ways. We're going to, for 0 up to L minus 1, and for every single m that is representable in I bits as an unsigned integer, we're going to define psi of IMS to be in this set. Because we're talking for ease of introduction, when I'm talking about this, I might just say psi IM. If m is fixed in the context, I might just say psi I. Okay, that's just so that I don't choke on my words. Psi IMS is going to be defined as this set right here. It's the set of delta mi evaluations at specific points. What are these points? Basically, it's omega c for c ranging in this set, which is 2 to the I, 2 times 2 to the 0, 2 to the I, 2 times 2 to the I, 3 times 2 to the I, 4 times 2 to the I, all the way up to this max thing times 2 to the I. Okay. Each of these psis is a set of psis 2 to the L minus I. Another definition, psi of LMS is going to just be the mth novel basis coefficient, and it's a singleton set. It's also technically of size 2 to the L minus L, which is 2 to the 0, which equals 1. Okay, our goal is to transform psi L0s up to psi L to the L minus 1s. In other words, the coefficients of the novel polynomial basis into psi 00s. What is psi 00s? That's a set of psis 2 to the L minus 0. So a set of psis 2 to the L, turning 2 to the L things into 2 to the L. And what are those 2 to the L things? They're actually evaluations of delta 00 at these points WC. What is WC? Well, when I is equal to 0, then it's literally like what we're gonna have if I just unroll it, and maybe I'll just like write it out so it's very clear, is this is going to be equal to the set of delta 00 W, let's say S is 0. And this will be like W0, delta 0, 0, W1, all the way up to delta 0, 0 of W 2 to the L minus 1. It's going to be this set. And just for clarity, I'll say this is D0, this is D2 to the L minus 1. When S equals 0. Okay, so our goal is to transform novel polynomial basis coefficients into this thing, and this thing is this 2 to the L size set, which is equal to delta 0, 0 evaluations on omega 0 up to omega 2 to the L minus 1. But what is delta 0, 0? Delta 0, 0 is actually, as we talked earlier, the same polynomial as capital D. So this is evaluations of D at 2 to the L different places. That's really cool. Great. So let's fix a parameter I. We're gonna talk about how you can sort of go from this to this in steps. Let's fix a parameter I, okay? And we'll now show how you can relate psi of IM. We'll also fix an M. We're gonna talk about how you can relate psi of I to psi of I plus 1. Okay, how does this work? Fix an M. Psi of I can be broken up into psi 0 of I and psi 1 of I. Kind of like the first half and second half is how you can think of it, sort of. Where psi 0 of I is these delta mi evaluations at WC, and psi 1 of I is these delta mi evaluations at WC plus W2 to the I. This can equivalently be written, of course, as WC plus 2 to the I. And linearity also exists on L as well, because L is also like this in vector space. Anyway, cool. So we've broken psi of I up into two parts. Now let's fix some B. So B is going to sort of be our index into this set. Weird wording for a mathematician, but whatever. So how do we figure out what the Bth value of psi 0 is and the Bth value of psi 1? So recall that psi of I plus 1 is going to have size half of psi of I. Psi of I is going to have size twice of psi of I plus 1. What's going to happen is that these two elements here for a fixed m, but psi of I plus 1 will have twice the number of m's. There's some weird patterns going on here. I think it's just clearest if I tell you exactly what the pattern is. Psi 0 of IMS, the Bth value of it, can be written as an expression using the psi I plus 1 ms, the Bth value, and psi I plus 1 m bunked up by 2 to the I s, the Bth value. And psi 1 of i's Bth value can be written with psi I plus 1 m plus 2 to the i's Bth value. And what you had already computed here. Okay, what's the takeaway? The takeaway is that for each I that's fixed, so we're in a specific round is how you can think about it. Make more sense later when we look at the algorithm. For each fixed M and B, we want to figure out what psi I is for that B and that B shifted up. And it can be derived from psi I plus 1 at that B and psi I plus 1 with the M shifted up at that B. Okay, clearly there's some nice patterns and structures going on here, and it'll definitely take you reading this a couple times to fully appreciate what the patterns mathematically here are. But algorithmically, it's clear what the patterns are. Using just some sort of factor and two previously calculated values, we can calculate two new values. And specifically structurally, what it looks like is the process to convert from like y0, y1 into x0, x1, where this is x0, x1, what we want to create, and this is what we already have. Looks like these two lines of code. Y0 plus some factor times y1. And then once we've computed x0, we can reuse it here. X1 equals x0 plus y1. Just one multiplication happens here only. Pretty nice. We care about reducing field multiplications as much as possible. So this little box here is some factor depending on what round you're in, I, and what like specific value you're trying to calculate, B is. This is sometimes called like the block index. So I is sometimes called the round and B is sometimes called the block index. In our code base, this little like square thingy here, this factor is called the twiddle factor. And specifically, twiddle factor for the ith round and the bth indexed block is this thing right here. The normalized subspace polynomial evaluated at this point in our binary field L. Crazy. Everything feels like it's connected. It will take some effort for this to really, really sink in though. But the key thing is the structure. Now, I'd recommend that you pause here, you take a look over the details at least once or twice before we continue on. But I will say that the next part will sort of emphasize some of the punchlines from this algorithmic structure part a little bit better. So it wouldn't be the craziest thing to watch the next part and then go back to sections 3, 3.5, and 4 again. So depending on your choice, high again after 3 seconds or high again after several minutes, we are now at section 4, the forward transform. Recap, we have fixed binary field L, degree R over F2 with this basis. We fixed the parameter little l, which basically defines our degree bound for our polynomial ring. And we have fixed an arbitrary polynomial, which is represented to us in this coordinate vector with respect to the novel polynomial basis. Our goal is to take as input this coordinate vector and as output like a different coordinate vector, which really is like the Lagrange basis coefficients over some domain. In English, evaluations of the polynomial in 2 to the L different places. And we want to do that in time O of L times 2 to the L. We now introduce the butterfly diagram. So let's look at this butterfly diagram rather than giving a robust definition. I think it's easier to just like work with a specific example. Here we have as inputs y0 and y1, and we're going to set x0 to be y0, this node's value, times 1, the edge's value, plus y1, node's value, times edge's value, 5. X0 is going to be set 1 times y0 plus 5 times y1. X1 is going to be set as 1 times y1 plus 1 times x0. So that's what the butterfly diagram is. I would recommend getting comfortable with this diagram before we move on. Here is the same diagram, except written a little bit differently. I've omitted all of the 1 factors because they're silly. And I've used a different color to indicate when the factor on the edge is non-1. And the color will sort of tell you what that factor is. Here, this is 5. Red is 5. Okay, get comfortable with this before we move on. This butterfly diagram. Now we're going to look at an example of the forward transform, because why look at the general thing first? Here, little l is equal to 3, and we have some arbitrary shift s. Again, you can keep pretending like the shift s is 0 for now. Once we actually need to use it, then you can come back and reread these notes thinking about s not being 0, but for now, just think about it as being 0. So we actually have L stages to our algorithm. And in each stage, we go from psi of L, and a bunch of values related to psi of L, to a bunch of values related to psi of L minus 1, to a bunch of values related to psi of L minus 2, to a bunch of values related to psi of L minus 3. And in this case, L was 3, so psi of 0. And this is exactly like what our goal of the forward transform was, to do this transformation. Because I'm like kind of bad with colors, I have made these arrows different values depending on which stage. So you can think about this as being like the L minus 1th stage of this algorithm, and this being the 0th stage. We claim that each of these stages, and maybe it's just clear to see with the butterfly diagram, takes time O of L, O of 2 to the L, sorry. There's 2 to the L elements here. And there's L stages. So this whole algorithm will take L times 2 to the L time. Okay, and this red is like this factor. This red is a different red, and it's this factor. This blue is a different blue, and it's this factor. Sorry, so this arrow is for these factors. Okay, I'm gonna make this clearer. I'm gonna do this. I'll do this. And I'll do this to make it really clear which arrows have which weight, which edges, directed edges have which weight. Cool. I will make a bold claim and say that this diagram above actually suffices as a complete algorithmic description for the L equals 3 case. Yeah, if you understand what the butterfly diagram is telling you programmatically, then this is sufficient as an algorithm description. And maybe it's clear how this generalizes to bigger L's. And if it's not, take a look at the code, and hopefully it'll be clear. Some more things. I talked about this. This is sometimes called the round or the stage of the butterfly. And then you can think about there being blocks. So in the L minus 1th stage, there's this block of size 2 to the L. In the next stage, there's 2 blocks of size 2 to the L minus 1. So you can think about this as having block index 0 and block index 1. Then there's the 0th stage, where there is like 2 to the L minus 1 blocks, each of block size 2. So this is like block 0, block 1, block 2, block 3. And depending on which stage you're in and what your block index is, that defines sort of what your twiddle factor is going to be. Cool. That's all I wanted to say about that. So twiddle factor actually turns out, like, what are you evaluating on? Again, pretend S is 0. It's like omega of block index times block size. Omega of block index times block size. I sort of talked about that vaguely here. This is the block size. This is your block index. Okay. Now, I guess the only thing more for an algorithmic description you would really need is how you can compute these W hats, these normalized subspace polynomials. What you can do is you can pre-compute them on all the basis vectors. And then if you ever need something that's not a basis vector, you can sort of do some additions. But we don't care about additions so much because like field multiplications are really the scary thing from a performance-wise. You could also pre-compute them at all of the elements of L rather than just the basis elements of L. Yeah, potato, potato. I'll talk about how to compute them at the basis elements. You basically do this sort of DP-like thing where you can start by computing the non-normalized subspace polynomial W0 at each of these basis elements. And that's easy to do because W0 is just simply the identity map. And then for each I, you can compute Wi at beta I onwards by looking back at the previous non-normalized subspace polynomial. And you use this like identity that we talked about in section 1 at the end, this lemma. Cool. And then once you've computed all the non-normalized subspace polynomials by this point, you can just normalize them. You'll notice we never bothered to compute like W4 of beta 2. There's no point to doing that because W4 of beta 2 is just going to be 0. Cool. Given all these normalized subspace polynomial evaluations at the basis vectors of L, our field, our binary field, we can use the linear property of the normalized subspace polynomials to calculate the normalized subspace polynomial at any arbitrary element that might not just be a basis element. Cool. And this will only involve additions of values, not multiplications. So we don't worry about the fact that its answer wasn't stored in our pre-computation. Cool. That concludes section 4. We talked about the forward transform, and if you understand this, you're in great shape. I would recommend pausing here and trying to, review everything that we've learned from section 1 to section 4 so far. And once you're comfortable with that, we'll move forward into section 5. Hi again, welcome to section 5. Now we're going to talk about linear codes. This section is going to be kind of like a detour and maybe not connected fully to what we've been talking about so far, but I think it's important nonetheless to talk about this, and I'm sort of using it as an excuse to talk about linear codes so that we can jargon bust a little bit. I think it's really important to be comfortable with the terminology and some of the basic ideas around linear codes. Linear code is a code that's a subspace of a vector space over a finite field F. Namely, if our code C is a subset of f to the n, and we have two x elements that are in the code, x and y, then for all scalar multiples a and b, scalar coefficients, ax plus by is also in the code. Special case that's interesting is actually when you set a is equal to 1 and b equal to -1, x minus y is in the code too. Another definition, the Hamming distance function takes as input 2 words of length n, and it returns a value from 0 to n inclusive, which is just the number of positions that those two length n vectors disagreed. The dimension of a code C is simply the dimension of C viewed as a linear subspace, and it's usually denoted by K. Recall that if K is a C is a K-dimensional subspace of f to the n, then that means that there exists a matrix G with K rows and n columns, such that every element of C is the result of taking some K-length vector over F and multiplying it by its generator matrix. So I said generator matrix, but that was basically the punchline. G is nothing, not just a random matrix, it's actually something we call the generator matrix in coding theory for linear codes. Specifically, our message can be any arbitrary vector of length k with symbols that come from f. So k symbols that come from the field. And when we multiply that row vector by this generator matrix, we get some code word. Let me say a few things just because they're interesting. They might be obvious. This code C, this code word rather, is a linear combination of the rows of G, where the coefficients come from this message. And more generally, the code C is the span of the rows of the generator matrix. In other words, every code word, the code is basically all of the code words that you can get, all of the, different linear combinations of generators rows that you can make using coefficients that come from F. Row vector times a matrix equals another row vector And this row vector is like a linear combination of the matrices rows with these coefficients. Okay. Just really like emphasizing that. That might be obvious to some of you. Apologies if that was too verbose. Technical note, if you're curious, you should look up something called a parity check matrix. This is really interesting in linear codes. And specifically what it's useful for is like, if you're thinking about these codes for like error correction, where I'm sending bits across a faulty wire and some of them get changed, and then I want to figure out what the original message was by decoding with errors, then this parity check matrix is a very useful way to think about a code. Like you can think about a code as being specified by its generator matrix, or you can also specify a code by its parity check matrix. The reason I'm not talking about it much here is because in cryptography, we don't use the codes necessarily for their error correction ability, more so as their redundancy. Specifically in cryptography, what you want to do is like, hey, is this message equal to the message that I expect it to be? And in order to do that, you would need to check it at every single place. If you miss a place, an adversary could have put the difference there. But what you can do with coding theory and like adding redundancy essentially is you can blow up a small message into a big code word. And if two messages are different in even one place, their code words will be different at a lot of places. Now you don't need to check everywhere in the code word to be reasonably certain that your message was what you expected it to be. And because that's how we usually use codes, I'm not talking about the parity check matrix for now. But if you're interested in coding theory, just beyond the context of snark design, you should definitely look up what a parity check matrix is. It's pretty cool. So after that aside, another definition, the distance of linear code is the minimum over all pairs of different code words of the distance between those two distinct code words. Equivalently, that's equal to the minimum Hamming weight of a specific code word. And Hamming weight is like the distance, Hamming distance between that word and the zero vector. Basically, how many coordinates are non-zero. And as a challenge, you should convince yourself of this equivalence when it's a linear code. And as a hint, you can basically do this with what I've said on this page alone. But as a challenge, convince yourself of this equivalence. Great. Distance of a code is usually denoted as little d. A linear code C of dimension k and distance d is denoted as a NKDQ code. Now there's this important lemma. There's a lot of interesting lemmas, but this is the one I'll highlight. Singleton bound states that for every NKD linear code, this inequality holds true, that the distance is upper bounded by n plus 1 minus k. When a code achieves equality, it's called MDS, or maximum distance separable, and it's a very desirable property in codes. You want the distances to be big. And the rate of a code, rho, is defined to be k over n. And it's sort of a measure of how space efficient this code is, how little redundancy it has. So take a look at these relationships. And the rate of a code is a value in 0 to 1, exclusive on the 0, of course. Sometimes we care about the inverse rate, which is a value in 1 to positive infinity. Inverse rate is equal to 1 over rho, just to be very clear. Great. So that concludes a very quick section about linear codes. Please review this before we move on to section 6. Now we will finally talk about Reed-Solomon codes specifically. So fix some domain D of n distinct elements in your field, FQ. We can define the Reed-Solomon code, nk some distance, to be this set, which is the set of vectors of evaluations at your domain place of some polynomial which is satisfying the degree bound, strictly less than k degree. Some facts. Reed-Solomon codes are linear. Why is this true? Well, it's because of this fact about polynomials, like p of x0 plus q of x0 is equal to p plus q of x0. Stop. If this is not sitting right with you, this fact, then take a minute, take out a pen and paper, and write out p of x is equal to this, q of x is equal to this, r of x is equal to something that's like the sum of p and q, and convince yourself that for all x, px plus qx is equal to rx. Interestingly, I've chosen to write out p and q and r in like the monomial basis because that's what we're most comfortable with for univariate polynomials. But if you were to write it out in some other basis, namely some Lagrange basis, then it becomes very clear. This fact is true basically like almost definitionally. But I would recommend just really convincing yourself of it. But because of this, Reed-Solomon codes are linear. Okay. Reed-Solomon codes are also maximum distance separable, so their distance is always equal to n plus 1 minus k, achieving the singleton bound. Why? Polynomial magic. Two distinct polynomials of degree at most k minus 1 can agree on at most k minus 1 places. So if you've chosen like a total of n distinct places to evaluate the polynomials on, they must disagree at least n plus 1 minus k places. Therefore, since they're MDS, there's no reason to write NKD like the D is kind of always the same. We can instead write RSNK to denote a Reed-Solomon code with message length K and code word length N. Now, here's where we're going to start to tie things together. What happens when N is equal to K and the distance is equal to 1? Does this mean that the message is its own code word? Well, not necessarily. It just means that you're turning something of length k into something of length k. There's no reason to believe that has to be the identity map. Of course not. You might say like, well, why wouldn't you just use the identity map in this case? Well, if you're using the codes for like a normal purpose, then like error correction, then yeah, like it seems kind of stupid to do any work in turning like a k vector thing with no redundancy into a k vector thing with no redundancy. But we're not doing it for error correction. We're doing it for other purposes. So for now, like there's still some encoding that takes place when you take a k vector, k length vector, and turn it into another k length vector message and the code word, and they're not necessarily the same. We're given the message, and we can interpret it as polynomial coefficients for some basis. And our encoding can be such that for a Reed-Solomon, where we interpret it as some other basis, right? If our original basis was not a Lagrange basis over some domain, and our like new basis for which Reed-Solomon is defined is not also a Lagrange basis for the exact same domain, then this encoding is not the identity map. It is doing some sort of a change of basis from something, some like coordinate vector, some basis representation into the specific Lagrange basis representation code word that I care about. Okay, and the output is like k evaluations of some polynomial over some domain D, or coefficients of P, univariate Lagrange basis with respect to D. Quick like recap, the basis looks like this, and each one of these guys is called like a Lagrange polynomial. And Lagrange polynomial is when evaluated at something inside the domain equals 1 if it's like, the thing that it was an indicator for, and it's 0 if it's anything else. This means like D set minus xi, so everything in D except for xi. Lagrange basis polynomials are basically like indicators. Okay, so when n equals k, the encoding function for Reed-Solomon codes is just a change of basis into Lagrange basis from whatever we had before. In fact, Reed-Solomon is a linear code, so for specified parameters, there exists a generator matrix G such that the encoding function to take a message into a code word is just message turns into message times generator function. And this G actually happens to be that change of basis matrix. Typically, when we do a row vector times matrix, this takes theta of n squared, where this matrix in this specific setting happens to be squared because k equals n. But we have a nice G with some great structure somehow embedded that allows us to do this like linear mapping in time less than O of n squared. When our bases are chosen well, this can be actually time O of n log n. Cool. Seems like stuff is starting to tie together maybe. For us, the field that we're working with, the finite field we're working with, is like f2 to the 2 to the I, which we call like the iota tower binary field. So our message will be k coefficients with respect to the novel polynomial basis, and that's how we'll interpret the k length vector message. And our code word will be k coefficients with respect to the Lagrange basis coefficients over some carefully selected D domain of size k. What about when k is not equal to n? Well, we will support only, for now, little k and little n as powers of 2. And n has to be less than 2 to the 2 to the iota. Why is this true? Okay, I'm going to go on a little bit of an aside now. Because for Reed-Solomon, if you need a domain of size n, then there needs to at least be n points in your field, right? And this sort of restriction is why people before Jim and Ben were struggling with this embedding overhead of trying to create multilinear commitment schemes based on the Fry protocol. Fry, the R is Reed-Solomon. For multilinear polynomials whose coefficients were, say, like f2, because they couldn't do the Reed-Solomon part over f2. They had to like embed f2 into something big enough so that their n was less than 2 to the 2 to the iota. Okay, let's say that n is equal to 2 to the capital R times k. And since n and k are both powers of 2 and k is less than n, this is like well-defined for capital R being some natural number, 0, 1, 2, 3, 4, etc. Here, capital R is log inverse rate. This. You take k over n, and you define that as rho, then capital R is equal to this. Okay. We will let our domain be the set of all field elements in t iota that are like associated with the first n binary numbers. Remember, because we talked about our field basically being like a vector space over f2, and then there was this like nice equivalence between a binary number and a field element. So that's what our domain, our carefully selected domain, is going to be for our code, our Reed-Solomon code. But interestingly, as before, recall that not only is this domain a subset of t iota as sets, but it's also a subspace of t iota when you view t iota as this like vector space over f2. D is specifically the subspace spanned by the first log n, and when I say LG, that means log base 2. First log n basis vectors, elements of t iota. D can be partitioned up into 2 to the capital R equally sized subsets that look like this, right? So D0 is basically everything you can create with everything from basis k, basis log k onwards set to 0. D1 is everything you can create in D0, but shifted up by omega k. D2 is everything you can create from D0, but shifted up by omega 2k. And I might even like make this very clear. Like, what is omega k? Omega k is equal to basis of k, log k. And what is omega 2k? This is basis of log k plus 1. What is omega 3k? This is basis of log k plus basis of log k plus 1. Interesting. It's like you're playing with like the kth bits onwards get to be variable, and that sort of defines like which of these sets you're in. But the first k bits are allowed to be free, or sort of like hard to explain. Like D0 is basically everything you can do with the first k bits. D1 is like everything you can do with the first k bits, but after that, not everything is zero. Specifically, the kth bit has to be 1. Then this is like first k bits are whatever you want them to be. But specifically, the k plus first bit must be 1. Like in this regime, all the bits from index k onwards have to be a specific thing, but all the bits from index k minus 1 before are allowed to like vary, and that's what this set is. And these things are called cosets. And there's an algebraic like formalization to this, which I thought about and I decided it wasn't like worth explaining. I think it was more interesting to give the intuition, but how these things are all sort of like shifts kind of D0, this like normal domain that we're used to. So we can partition D into these 2 to the R equally sized subsets, or also called like cosets, which is like subset with more structure, in fact. And they're all the same size, and everything, all the elements in these cosets are like, every element belongs to like exactly one coset. Note that like D is in fact this disjoint union, and that for every pairwise, these DIDJs have an empty intersection. This is exactly what partition means. And each of the DIs have the same size of K. Cool. So now what does our Reed-Solomon over binary field encoding algorithm look like? We take as input a message, M, which is a K-length vector, which we will interpret for our algorithm as coefficients with respect to some novel polynomial basis. And our algorithm will be start with a code word as the empty array, and for each coset shift in 0 to 2 to the r minus 1, we will calculate a chunk of our code word, which is the additive NTT on the message with some shift parameter s set to our coset shift times k. And we'll extend the code word with this chunk that we created. We'll return the code word. So we're doing 2 to the r loops, and each of these loops is an additive NTT, which takes time k log k. So it takes this much time, and k times 2 to the r was what we defined n to be. So it takes n log k time. Very cool. Let's zoom in a little bit and figure out what this like line of code is doing. This chunk equals additive NTT ms. Well, it's doing this forward transform where little l is equal to log base 2 of k. In this example, k is equal to 3, and we have some arbitrary s. It's exactly like what we had done before. And what is this at the very end? What this is at the very end is this again. So this here is like D0, D1 up to D7, the novel basis coefficients for our specified polynomial. And here, this at the end is like D evaluated omega 0 plus omega s. D evaluated at omega 1 plus omega s, all the way down to D evaluated at omega 7 plus omega s. And now when we set like omega s to be something like huge, like I don't know, like coset shift times k. So in this case, k was 3. So like let's say that we set s to be like I don't know, let's say sorry, k here should be 8. What am I talking about? So here, let's say we set s to be like, I don't know, 16. Then this is like the evaluations over D2, right? Which is like W16 plus D0, that coset, or equivalently like W2 times K plus D0. So that's exactly what's going on. Like each of these chunks is getting evaluations for like, well, when I talk about them as binary numbers, the field elements are like 0 up to k. Then it gives you the evaluations from k up to 2k. Then it gives you the evaluations of 3 up to 2k up to 3k, et cetera, et cetera. That's really cool. And by the end of this, you get the evaluations from 0 up to n. Pretty awesome. Exclusive on the n. 0 to n minus 1 inclusive. So that's section 6. I would take a second and try and fully internalize what just happened here. Now, a quick note on the inverse transform and decoding. You can decode from any chunk using INTT. It's preferable if you use like one coset. Like obviously, if you have a polynomial that's degree bound is strictly less than k, then with any k, input-output pairs, you can figure out what the polynomial is. And yes, you can decode using INTT using any of these chunks of size k. If you want to make your life easy, you choose the chunk to be like something that's sort of contiguous, like evaluations from k to 2k minus 1 or 2k to 3k minus 1. And the inverse transform follows, sorry, the exact same structure, just starting from this guy and turning us into this guy. Right, so we're starting from like the code word kind of from before, yeah, the code word, and we're turning it into the novel basis polynomial coefficients. And what S is depends on like which chunk you chose. Cool. And yeah, that's everything. As a quick appendix, I put like the basic repeated local structure of the additive INTT here and the local structure of the additive NTT here. And when you like write these things out programmatically and you think about like what these maps are doing, this bivariate 2 to 2, like 2 values to 2 value map is doing on each side, they sort of cancel each other out, and composed with one another, they become the identity map, mapping like AB to AB, which means that they're sort of doing like the opposite things as each other. It's very cool. If you do try and verify this, don't forget that we're working in a binary field of characteristic 2, which means that x plus x is equal to 0 for any x. But yeah, that's pretty much everything. So I hope that you enjoyed this lecture. I hope you learned something. And I hope that you're able to like combine reading my notes with listening to me speak to be able to fully understand this material. I think it's really interesting and really cool. Feel free to ask me any questions, whether it's before I leave the company or after I leave the company. I'm very happy to help answer them. Last thing I'll note is that, yeah, this stuff is very hard and it's going to take a lot of effort on your side to try and understand this. I don't think that there's any way to passively learn this. You need to sort of get a little bit dirty with the details and feel like you understand it yourself. But I'm trying to help as much as I can with that with these notes in this lecture. But yeah, don't feel bad if this takes some time to learn. That just means that you're a normal person. And yeah, I think that this is really worthwhile learning. If you learn this well, it'll help you a lot in trying to understand the Fry protocol and a lot of other things that are interesting in the Snark space. And these themes will just keep coming back and back. So with that, I will wrap this up. And yeah, thanks again for listening, and best wishes to everyone out there.